This is stochastic process Mod-05 continuous time Markov chain. I am planning for 6 to 8 lectures in this model, and I am going to start the lecture 1 with the definition of continuous time Markov chain, then the derivation of Kolmogrov differential equations, and I am going to give some simple examples for the continuous time Markov chain, and also I am planning to give the stationary and the limiting distributions of continuous time Markov chain in this lecture. Let me start with the introduction of continuous time Markov chain. The continuous time Markov chain is a special case of a stochastic process. This is a stochastic process in which the Markov property is satisfied, therefore, it is called a Markov process. Based on the classification of a state space and the parameter space, whether it is a discrete or continuous, you can classify the Markov process. Suppose the state space is a discrete, then we say that Markov process is a Markov chain. Along with the state space is a discrete, if the parameter space is also discrete, then we say discrete time Markov chain. That means a stochastic process satisfying the Markov property, state space is discrete and the parameter space is also discrete. This we have discussed in the model 4. A stochastic process satisfying the Markov property whose state space is discrete and the parameter space is continuous, then that stochastic process is called the continuous time Markov chain, that we are going to discuss in the model 5. There are other type of Markov process also, which has the state space is continuous and the parameter space is also continuous, that is called the Brownian motion or Vernier process, that we are going to discuss in the model 7. Now, in this lecture we are going to discuss the continuous time Markov chain under model 5. Let me start with the definition of continuous time Markov chain. A discrete state continuous time, that means the state space is discrete, that means the possible values of the random variable going to take the value for possible values of parameter space, that is going to be finite or countably infinite. Therefore, the state space is going to be called it as a discrete. Continuous time means the parameter space or the possible values of the t, that collection is uncountably infinite. Therefore, it is called a continuous time, that means a parameter space is continuous. So, a discrete state continuous time stochastic process x of t for t greater than or equal to 0, need not be t greater than or equal to 0 also, but here I am making the very simplest one. So, the x of t for fixed t, it is a random variable, for every t, that collection, that is going to be a stochastic process, and the state space is discrete and parameter space is continuous, and that stochastic process is going to be called it as a continuous time Markov chain if it satisfies the following condition. If you take n time points, arbitrary time points, n plus 1 time points, that is a t naught to t n, you can say the t naught can be 0 also, and with this inequality t naught less than t1 less than t2 and so on tn, and you take the any arbitrary t, that is a tn less than t with this inequality. For fixed t, that x of t is going to be a random variable. Therefore, now we are going to find out the conditional distribution for this n plus 1 random variable with the random variable x of t. That means at t naught you have a x of t naught, that is a random variable. At t1 x of t1 is a random variable. Similarly, at tn x of tn is a random variable. you have n plus 1 random variable. With this n random variable given, that means it takes already some values with x naught, x1, xn, so on respectively, and you are finding the conditional CDF for the random variable x of t. So, that means you have a n plus 2 random variables taken at the arbitrary time points t naught to t n as well as small t. And you are finding the conditional CDF of the random variable x of t, given that already the other n plus 1 random variables taken at those arbitrary time points, it taken the value x naught, x1 and so on till xn, it is taken already these values. That conditional distribution, conditional CDF, if that is same as, again it is a conditional CDF of x of t given the last random variable x of t n is equal to xn. So, these n plus 1 time points are arbitrary time points. So, if it satisfies for all n, for every n, that means the conditional distribution of n plus 1 random variable is same as the conditional distribution of the last random variable. If this property is satisfied by the discrete state continuous time stochastic process for arbitrary time points, then that stochastic process is called a continuous time Markov chain. This is very important concept. This is called the Markov property. That means the t is a sort of a future. So, what is the probability that the random variable will be in some state at the future time point t, given that you know the present state, that is where the system is in time point t n, that is small x n, and I know the past information starting from x of t naught till x of t n minus 1. I know the information. That means what is the probability that future the random variable x of t will be in some state, given that it was in the states x naught at time point t naught, it was in the state x1 at the time point t1 and so on. Latest at the time point t n the system was in the state x n, that is same as what is the probability that the future the random variable will be in some state at time point t, given that it is now in the state x n at the time point t n. That means future given present as well as the past information is same as future given only the present, which is and independent of the past information. That is called the memoryless property or Markov property. So, since this property is satisfied by the stochastic process, which has the state space is a discrete and the parameter space is continuous, then that stochastic process is called a continuous time Markov chain. So, this is the definition. Now, we are going to give some more properties over the continuous time Markov chain and some simple examples, as well as the I am going to explain the limiting distribution and the stationary distribution for continuous time Markov chain in this lecture. Let me show the sample path over the time t, that is x axis, the y axis is x of t. So, the system was in some state at time point 0, it was in the same state for some time, then it moved into the some other state, then it was there in that state for some time, then it moved into some other state and so on. If you see the sample path, the following observation, the system can stay in some state for some amount of time, after that it will move to the some state. So, there is no equal interval of a system going to be in some state also, it can be some positive amount of time the system can be in the some discrete states. So, here the observations are the state space is discrete, whereas the parameter space is continuous and the time spent in each state, that is going to be some positive amount of time before moving into any other states. So, this is the observation in the sample path which I have drawn. Now, I am going for few notations to study the behavior of a continuous time Markov chain. Whenever the Markov chain, that means here it is a continuous time Markov chain, it is a time homogeneous, then the conditional probability of system being in the state j at time point t plus capital T, given that the capital T it was in the state I, that does not depend on capital T. Here we assume that the state changes from I to j at a future time point t plus capital T. This transition probability says the system was in the state I at the time point t. Let me draw the simple diagram. The system was in the state I at the capital T, then what is the probability that the system will be in the state j what is the probability that the system will be in the state j at the time point t plus t. It is independent of a capital T whenever the Markov chain is going to be a time homogeneous for any t greater than or equal to 0. That means that the actual time does not matter, only the length matters, the length of the transition time. That means the small t is matters, not the capital T whenever it is a time homogeneous. That we can denote it as a Pij of t, because it depends on only the interval, not the actual time. Therefore, it is a function of small t, Pij of t. That means that is the transition probability in the system. So, the same thing can be written as the Pij of t. This is a notation. What is the transition probability that the system was, what is the probability that the system will be in the state j given that it was in the state I at time 0. Since it is valid for any interval of t to t plus t, it is independent of capital T. Therefore, I can represent this transition probability as a probability that the system in the state j at time t given that it was in the state I at time 0. This denoted by Pij of t. So, this notation we should remember, it is a transition probability with the suffix 2 letters I comma j of t. This also call it as a stationary transition probability. Stationary means it is a time invariant, only the length of the interval is matters. Similarly, I am denoting the next notation pi j of t. The Pj of t is a conditional probability, whereas the pi j of t, that is a unconditional one. What is the probability that the system will be in the state j at time t? There is a possibility system would have been coming to the state j before time t for at time 0 itself, or it would have come before, just before t, whatever it is. This probability will give the interpretation. What is the probability that the system will be in the state j at time t? Only it gives the information at the time t. This is a unconditional probability. I need another notation for a initial state probability vector also, that is a pi naught. Pi naught is a vector which consists of entities. What is the probability that the system was in the state 0 at time 0? Therefore, this I can write it as pi j of 0, that is nothing but what is the probability that the system was in state j at time 0. So, this is the meaning of pi j of 0. What is the probability that the system will be in the state the system was in the state j at time 0, that is pi j of 0. Like with these entities you are framing the vector, that is pi naught. So, in this we are giving 3 notations. One is the transition probability p I j of t, that is a conditional probability. The other one is unconditional probability, that is pi j of t, and initial state probability vector pi naught. Using this, I am trying to find out what is the distribution of x of t for any time t. For any time t, x of t will make a stochastic process. Here it is a continuous time Markov chain. The default one is a time homogeneous continuous time Markov chain, and our interest is to find out what is the distribution of the random variable x of t. It has the probability mass function, that is pi j of t, and if you make a summation over S, where S is a state space, that summation is going to be 1. If I know the initial state probability vector with the entities pi I of 0, as well as if I know the transition probability of system moving from the state I to j from 0 to small t, I can able to find out what is the probability mass function of system being in the state j at time t. That is pi j of t, that is same as probability that x of t is equal to j, that is same as I can make a summation, I can make a conditional. What is the probability that the system will be in the state j at time t, given that it was in the state I, multiplied by what is the probability that a system was in the state I at time 0 for all possible values of I, where S is nothing but the state space. I know that I know that the probability of x of 0 is equal to I, that is same as pi I of 0, and this transition probability, since the Markov chain is a time homogeneous, so 0 to t, that is nothing but 0 to 0 is the time point and t is any time point, and I is the state in which the system was in the state at time 0. So, p I j of t, if I multiply pi I of 0 p I j of t for all possible values of I will get the probability that the system will be in the state j at time t. That means, if you want to find out the distribution of x of t for any time t, I need a initial state probability vector as well as the transition probability of system moving from one state to other states. This is given, usually the initial state probability vector is given. So, what we want to find out is p I j of t. So, how to find the p I j of t, that derivation I am going to do it in the another 2-3 slides. So, before going to the p I j, you see the sample path of a time homogeneous continuous time Markov chain. As I said, the system is staying for some positive amount of time in any state before moving into any other states. Our interest is what is the distribution or what is the waiting time distribution of system being in any state before moving into any other states. That is our interest to find out. So, how we are going to find out, that I am going to explain. That is called the waiting time distribution. That means what is the distribution of time spending in any state for a time homogeneous continuous time Markov chain before moving into any other states. I assume that at time 0 the system was in the state I. That means x of 0 is equal to I, that is known, or the probability of x of 0 is equal to I, that probability is 1. Let me make out the random variable tau that is a random variable denoting the time taken for a change of state from the state I. Change of state means it does not matter which state it goes, my interest is to find out what is the waiting time distribution for the state I, the time spent in the state I. For that, let me make a simple graph. So, this is a t and this is x of t. Suppose you assume that the system was in the state I at the time point 0. After some time, it moved into some other state. Okay. At the time point S, it was in the state I. At the time point t also it moved into some other state. So, the tau here is nothing but the time spent in the state I from here to here. So, that is a random variable. So, what I am going to do? I am going to find out what is the complement CDF for the random variable tau, that is what is the probability that the tau greater than s plus t given that x of 0 is equal to I. That is same as the probability of the tau is greater than s plus t given that I can introduce one more condition, tau is greater than s, then I can multiply by using the total theorem of probability, tau greater than s given that x of 0 is equal to I. That is same as the first one I can rewrite as the probability of tau greater than s plus t given that x of s is equal to I, because x of 0 is equal to I as well as tau is greater than s, where tau is the time spent in the state I. Therefore, I can make out x of s is equal to I by combining these two concepts multiplied by the probability of tau greater than s given that x of 0 is equal to I. That is same expression here. Now, the probability of tau greater than s plus t given that x of s is equal to I, that I can rewrite because this Markov chain is a time homogeneous Markov chain. So, the s to s plus t, that is same as the complement CDF of the random variable tau for the time t, because it is s to s plus t, since its Markov chain is a time homogeneous, only the length is matters, that is the interval of length t. Therefore, this is nothing but the complement CDF for the random variable tau at the time point t multiplied by this is nothing but 0 to s. So, this is the complement CDF of the random variable tau the time point s, whereas the left hand side is the complement CDF for the random variable tau for the time point s plus t. So, what we got, the result is the complement CDF of the unknown random variable tau at the time point s plus t, that is same as the product of complement CDF at the time point s and t. So, this is valid for all s and t greater than 0. So, we have to find out what is the random variable or what is the distribution going to satisfy this complement CDF at the time point s plus t, same as the product of complement CDFs at the time point s and t. If any distribution satisfies this complement CDF property, then we can conclude the random variable, then we can find out the distribution for the random variable tau. So, in this derivation we have used the time homogeneous property as well as the total probability rule, as well as we have used the Markov property. Therefore, it will end up the complement CDF satisfying this equation. Now, we have to find out what is the distribution going to satisfy this property. So, if you substitute any function with the e power any parameter lambda with the exponential of e power minus lambda t, the previous equation is going to be satisfied. The previous equation is going to be satisfied. This equation is going to be satisfied as long as the function is of the form e power minus lambda t, for lambda is greater than 0 and t is greater than 0. Since the complement CDF is e power minus lambda t, therefore, the CDF of the unknown random variable tau, that is 1 minus e power minus lambda t for t greater than 0 for some lambda. And you know that if the CDF of the random variable is 1 minus e power minus lambda t for t greater than 0 and lambda greater than 0, then that random variable is a exponentially distributed random variable. So, we can conclude the amount of time or the time taken by the system staying in the state I, that time is exponentially distributed. That is a continuous random variable whose distribution is exponential distribution with the parameter lambda. Even we can specify lambda suffix I, that means it is going to be a function of it depends on the I. That means if the random variable is going to spend in some state, and that is always exponential distribution with some parameter lambda, and that parameter lambda may depend on the state I. That means if I go back to the sample path, I can say that the time the system spending in this particular state, that is exponentially distributed with some parameter, then it moved into some other state. The time spending in this state, that is also exponentially distributed with some other, it could be some other parameter, it depends on that particular state. Then it moved into the some other state, and the time spending in this state, that is also exponentially distributed. And later we can conclude all these the time spending in each state, because of it is a Markov property satisfied, the time spent in this state, the time spent in this state, all are exponentially distributed, which is independent of the other. So, all are going to be mutually independent random variables, then only the Markov property is going to be satisfied. That means whenever the system is moving from one state to another state, you will have a exponentially distributed time spending in each state, and they are form a mutually independent. And since the exponential distribution has the memoryless property, the system spending in this state, if you just observe at any time t, and what is the probability that the system will be for some more time in the same state, given that it was spending already this much time in this state, then that is also exponential distribution because of a memoryless property of exponential distribution, and which is independent of how much time spent in the same state already. Therefore, the Markov property is going to be satisfied throughout the time, whether the system spending in this state or the other state and so on. So, the Markov property is going to be satisfied for all the time points, and the time spending in each state is exponentially distributed, and all the random variables spending in each state, all are going to be mutually independent random variables. Now, we found out what is the time spending in each state, and that is exponential distribution with some parameter lambda I, and the distribution is same for all I, whereas the value of the parameter lambda maybe depends on the I. Now, I am going to give few state transition diagrams for the time homogeneous continuous time Markov chain. You see the first example, it has only two states 0 and 1. So, the state space S is 0 comma 1 and the time spent in the state 0 before moving into the state 1, that is exponentially distributed with the parameter lambda. Once the system come to the state 1, the time spent in the state 1 before moving into the state 0, that is exponentially distributed with the parameter mu. Lambda is strictly greater than 0 and the mu is also strictly greater than 0. That means, you know, the exponential distribution has the mean 1 divided by the parameter. Therefore, the average time spent in the state 0 before moving into the state 1, that is 1 divided by lambda. The average time spending in the state 1 before moving into the state 0, that is 1 divided by mu. Since it is a 2 state, so over the time the system will be in the state 0 or 1, and you can classify the states also the way we have discussed in the discrete time Markov chain. Since both the states are communicating, both the states are accessible from each other direction, therefore, both the states are communicating each other. Since the state space is 0 and 1 and both the states are communicating each other, therefore, this is a irreducible Markov chain. For a irreducible Markov chain, all the states are of the same type. For a finite Markov chain, we have at least one positive recurrent state. Therefore, both the states are going to be a positive recurrent state. But here there is no periodicity for the continuous time Markov chain. Therefore, we can conclude the first example, both the states are a positive recurrent and the Markov chain is a irreducible Markov chain. So, the continuous amount of time system spending in state 0 and 1, that is exponentially distributed with the parameters which I discussed earlier. Now, I am moving into the second example. In the second example, we have a state space is countably infinite and the system spending in the state 0 before moving into the state 1, that is exponentially distributed with the parameter lambda naught. Whereas, in the state 1, the system can spend exponential amount of time, the amount of time spending in the state 1 before moving into the state 2, that is exponentially distributed with the parameter lambda 1, and similarly the system spending in the state 1 before moving into the state 0, that is exponentially distributed with the parameter mu 1. Therefore, this is mu 1 and this is lambda 1. Therefore, the time spending in the state 1 before moving into any other state, that is going to be minimum of the exponentially distributed with the parameter lambda 1, one random variable, you can call it as a x, and you can call it as another random variable, that is exponentially distributed with the parameter mu 1. Therefore, the amount of time spending in the state 1 before moving into any other state, that just now we have concluded that waiting time distribution is exponentially distributed, that will come from here also. So, here these two random variables are independent, x and y are independent random variables, both the random variables are independent. Therefore, the time spending in the state 1 before moving into any other state, that is going to be minimum of the random variable with the exponentially distributed parameter lambda 1 and the random variable which follows exponential distribution with the parameter mu 1. you know that the minimum of a 2 exponential, as long as both the random variables are independent random variable, then this is also going to be exponential distribution with the parameters, with the parameter lambda 1 plus mu 1, as long as both the random variables are independent and both are exponential. You can do it as a homework. Minimum of a 2 exponential are going to be exponential with the parameter lambda 1 plus mu 1. Therefore, the time spending in the state 1, that is exponential distribution with the parameter lambda 1 and mu 1. Also, one can discuss what is the probability that the system moving into the state 2 before moving into the state 1, that is a lambda 1 divided by lambda 1 plus mu 1. Similarly, what is the probability that the system moving into the state 0 before moving into the state 2, that is mu 1 divided by lambda 1 plus mu 1, that also one can find out. So, what is the conclusion here is the time spending in the state 1, that is exponential distribution with the parameter lambda 1 plus mu 1. Similarly, the time spending in the state 2, that is suppose if it is lambda 2, then lambda 2 plus mu 2. So, this is a one type of continuous time Markov chain. The third example, this is also continuous time Markov chain. This is sort of a two dimensional Markov chain with the labeling with the 0, 0, 1, 0, 2, 0 and so on. So, all the labeling which is parameters for the exponential distribution. So, the change from the discrete time Markov chain state transition diagram and the state transition diagram of a continuous time Markov chain, here there is no self loop and the labels are the parameters for exponential distribution, whereas the discrete time Markov chain, it is a one step transition probability going from one state to other states. Here the labels, the arrow gives the time spending in the state exponential distribution with the parameter lambda naught and moving into the state 1 and so on. Now, I am going to find out how, now I am going to find out the Pij of t. For that I am going to do the derivation starting with the Chapman-Kolmogrov equation. Let me start with what is the transition probability of system is moving from I to j during the time 0 to t plus capital T. That is nothing but what is the transition probability system will be in the state j at the time point at t plus capital T, given that it was in the state I at time 0. That is same as I can in between make some other state. I can make one more state k at time point t. For all possible values of k also I will get the same result. That is same as I can make a summation over k belonging to S is a state space. That is same as what is the conditional probability of system will be in the state j at the time point t plus capital T, given that it was in the state I at time 0 as well as it was in the state k at small t also, multiplied by what is the transition probability of system moving from 0 to t from the state I to k. That is same as the first conditional probability. You see, this is same as the Markov property which we have discussed in the definition of a continuous time Markov chain. There I have discussed the CDF, cumulative distribution function. Here it is the probability mass function, whereas this is a conditional probability mass function. What is the conditional probability mass function of system will be in the state j at time point small t plus capital T, given that it was in the state I at the time point 0 as well as it was in the state k at the time point t, and you know that 0 less than t plus capital T. because the way we made it is all these values are greater than 0. Therefore, by using the Markov property of a continuous time Markov chain, so this is same as what is the probability that the system was in the state k at time small t and move into the state j at the time point t plus capital T. Again you use the time homogeneous property. First you use the Markov property, therefore, this is a transition probability of t to t plus t moving from the state k to j. Then you use the time homogeneous property, therefore, only the length matters. Therefore, t to t plus capital T, that is same as 0 to capital T. Therefore, the system is moving from the state k to j from 0 to capital T, that is a p k j of t. The second one, it is a transition probability, system is moving from state I to k during the interval 0 to capital T. Therefore, this is I to k of t. So, this is valid for all I comma j with the t greater than or equal to 0 and capital T is also greater than or equal to 0. Therefore, the left hand side is the transition probability of system is moving from the state I to j from 0 to t plus capital T, that is same as summation over, I can rewrite in a different way, I to k in the interval 0 to small t, k to j instead of small t to small t plus capital T, because of the time homogeneous I am just making 0 to capital T. Therefore, this is valid for all values of k summation. This equation is called the Chapman-Kolmogrov equation for a time homogeneous continuous time Markov chain, because here for this transition probability we have used Markov property as well as the time homogeneous property also. Therefore, this is a Chapman-Kolmogrov equation of the transition probability of system moving from I to j in small t plus capital T can be broken into product of these for all possible values of k. So, like this you can break it many more ways with the summation for all for different state of k. Using these we are going to find out the transition probability of p I j of t. You remember, to find out the distribution of x of t you need a initial state probability vector as well as the transition probability p I j of t. The initial state probability vector is always given. You have to find out the p I j of t. Once you know the p I j of t, you can find out the distribution of x of t for any time t. For that, I am going to define the quantity called q I j, and later this is going to form a matrix that is going to be called it as a infinitesimal generator matrix. So, let me start with the definition. Q I j, that is nothing but take a derivative of p I j of t, that is a function of t. You can find out the derivative, it is differentiable function only. So, you take a derivative, then substitute t equal to 0 for all I not equal to j. Then you define q I, that is also in the same way separately, because the q I, the diagonal element is going to be different from all other elements, therefore, I am defining separately. You know how to find out the derivative of p I j of t with respect to t, that is nothing but the limit delta t tends to 0, the difference divided by the delta t. Since p I j of t is the transition probability of system moving from I to j, you can use p I j of 0 is equal to 0 for I is not equal to j, for j is equal to I, that is p I of 0, that is equal to 1. That means, what is the transition probability of system moving from the state I to I in the interval 0, that is same as 1, that probability is 1. So, use this in the previous limit in this p I j of 0 is equal to 0 and p I of 0 is equal to 1, you substitute, then the limit delta t tends to 0. Therefore, the p I j of delta t, this will go to this side. So, q I j times delta t. Therefore, this is going to be p I j of delta t is nothing but the q I j multiplied by delta t plus small o order of delta t, That means, as delta t tends to 0, this whole quantity will tends to 0. Similarly, you substitute Pii of 0 is equal to 1 here, therefore, Pii of delta t, that is same as this will come to this side. So, 1 plus Qii delta t plus order of delta t. So, this order of delta t, that also tends to 0 as delta t tends to 0. You know that the summation of Pij even at the time point delta t, the small negligible time point delta t, at the time also over the I, that is equal to 1. Therefore, if you sum it up, you can conclude the left hand side is the probability, right hand side for I is not equal to j, you have Qij, whereas the second expression you have 1 plus Qii. Therefore, using the property of summation of Pij is equal to 1, you will get the summation of Qij for all I, for all j, that is going to be 0. When you add both the equations for all j, you will get the summation over j Qij is equal to 0, as well as all the Qij quantities are going to be greater or equal to 0 from the first one, because the left hand side is a probability and this is multiplied by the delta t is always greater than 0. Therefore, the Qij is going to be greater than 0 for all I not equal to j, whereas if I add over all the j, that is going to be 0. Therefore, you will get the Qii, that is nothing but you make the summation for all Qij for all j except I, then you make a minus sign. So, that is going to be the Qii. That means, the diagonal element is nothing but you make the row sum except that the diagonal term and put the minus sign, that is going to be the diagonal term. Therefore, when you make a row sum, that is going to be 0. The details of the proof can be found in the reference books. So, the quantity Qij that has the property, the row sum is going to be 0 and other than the diagonal elements are greater than or equal to 0. Therefore, the diagonal element is going to be summation of all the other terms with the minus sign. So, using this we can make a matrix that is going to be a Q matrix with the entities Qij such that satisfies the property Qij is always greater than or equal to 0 for I is not equal to j, whereas the diagonal element is minus of summation. Therefore, it has the property the row sum is going to be 0. So, the difference between this matrix and the one step transition probability matrix in the DTMC, that is a probability matrix. So, the entries are probability values from 0 to 1 and the summation row sum is 1, whereas here because Qij's are obtained by differentiating the Pij's. These are all the rates and these rates are always greater or equal to 0 other than the diagonal elements, and the diagonal elements are minus with the summation of all other row elements. So, this matrix is called the infinitesimal generator matrix. Some books they use the word rate matrix also, and whereas here the rates are placed in the other than the diagonal elements, and the sum of the rates could be 0. That means, the probability of a system moving from that particular state to that particular state is not possible. That probability is 0, or there is in a small interval of time there is the transition is not possible. So, whenever the rates are greater than 0, that means there is a positive probability that the system can have a transition of system moving from I to j. So, we have defined the Q matrix. Now, using the Q matrix we are going to find out the Pij of t. So, let me start with the Chapman-Kolmogrov equation. Now, I am going to differentiate with respect to capital T. That means, I make the interval 0 to small t plus capital T as a 0 to t, then I make a t to t plus capital T, differentiate with respect to capital T. Therefore, the left hand side is going to be I have written with a dash. So, the derivative comes inside the p k j of t, then I am substituting t equal to 0. So, basically I am making a system to move from state 0 to small t, then there is a small interval of time from t to t plus capital T, that is the meaning interpretation of this. Then substituting t equal to 0, I will get the left hand side is going to be p I j of dash t, that is same as the summation over this, whereas this is nothing but the way we have defined the infinitesimal generator matrix entities. So, this is nothing but the q k g, that is the rate in which the system is moving from the state k to j. In a matrix form, I can make it as a p I j of t is going to form a matrix. So, the p dash of t, that is same as a p of t times q. So, this is the matrix and the p of t is also matrix, and this is the p dash of t means each entities are differentiated with respect to time t. So, this is in the matrix form, and this equation is called the forward Kolmogrov differential equation, because the derivation goes from 0 to t, then t to t plus t we are considering as a very small interval of time. Therefore, this equation is called a forward Kolmogrov differential equation. The same way, if you do 0 to small t, that has a small interval of time, and t to t plus capital T, then I will get the p dash of t is equal to q times p of t, that is called the backward Kolmogrov differential equation. Whether you frame a forward equation or a backward Kolmogrov equation, if you solve that equation, you will get the p I j of t. If you solve p dash of t is equal to p of t into q, that is a forward equation, p dash of t is equal to q times p of t, that is a backward equation. If you solve the equation with the initial condition, because it is a differential equation, so you need an initial condition, what is the probability, what is the transition probability of system moving from I to j at time 0. If you know the initial condition, by supplying that, solving this equation, you will get the p I j of t. Once you know the p I j of t, then you can get the distribution of x of t. So, once you know the p I j of t, the given is pi I of 0, and by solving that forward or backward Kolmogrov differential equation, you will get the p I j of t. Using these two, you can get the pi j of t. So, for a given pi I of 0 and p I j of t, that means the transition probability and the initial state probability vector, one can find out the distribution of x of t. So, in this lecture, I have started with the Markov process, then I have discussed the definition of a continuous term Markov chain, and also I have given what is the distribution of time spending in any state before moving into any other state, and also I explained the infinitesimal generator matrix, and using that how to find out the transition probability of p I j t from the Chapman-Kolmogrov equation, and we got a forward as well as the backward Kolmogrov differential equations. By solving a forward or backward Kolmogrov differential equation, one can get the one can get the p I j of t, that is a transition probability. Using this equation, you can get the pi j of t, that is nothing but the distribution of x of t. With this, let me stop this lecture, and the next lecture I will go for a simple example of a continuous time Markov chain, as well as the stationary limiting distribution and the steady state distribution in the next lecture.